Beneath your feet lies an internet that's been operating for millions of years. It's not made of fiber optics or copper wire, but of living cells and fungal threads. This is the Wood Wide Web, nature's original internet, and it's revolutionizing our understanding of intelligence, communication, and network design. Picture a forest floor. What appears to be a carpet of fallen leaves and soil is actually the surface of an inconceivably vast network. Every tree, every plant, is connected through an intricate web of fungal filaments called mycorrhizal networks. These microscopic threads form an information superhighway that makes our most advanced computer networks look primitive by comparison. In a single cubic inch of soil, you might find hundreds of miles of fungal threads, all transmitting information and resources between plants. This network processes more data per second than all of humanity's internet traffic combined. And it does so without servers, without cables, and without any central control. Let's dive deeper into how this natural internet works. When a tree is attacked by insects, it doesn't just defend itself, it warns its neighbors. Through the fungal network, it sends chemical signals that travel to surrounding trees, allowing them to prepare their defenses before the insects reach them. This early warning system operates with a sophistication that our best cybersecurity systems still can't match. But the network doesn't just transmit warnings. It's also a resource-sharing platform that would make any Silicon Valley startup envious. Older, larger trees nicknamed mother trees by scientists act as hubs in the network, supporting younger trees with nutrients and water when they're in need. These forest elders can recognize and preferentially help their own seedlings, demonstrating a level of network intelligence we're only beginning to understand. The implications of this discovery are staggering. While we've been proud of developing peer-to-peer networks and cloud computing, nature has been running a far more sophisticated system for millions of years. In the forest's living internet, every node is both a sender and receiver, every connection is dynamic, and the entire system is self-repairing and self-optimizing. Consider how this network handles resources. When one area of the forest is rich in nitrogen but poor in phosphorus, and another area has the opposite, the fungal network facilitates trade. Plants share resources not through central planning, but through a dynamic market economy that responds instantly to supply and demand. It's as if nature invented blockchain technology eons before we conceived of Bitcoin. The scale of this operation is mind-boggling. A single fungal network can connect hundreds of trees across acres of forest. These connections aren't random, they form what network scientists call a scale-free network, the same structure found in our social media networks and the human brain. It's a design that maximizes efficiency while maintaining resilience. But the sophistication of nature's network goes beyond its architecture. The fungal internet is also a learning system. When one plant discovers an effective defense against a pathogen, it can share this information through the network, allowing other plants to adapt their chemical defenses accordingly. It's like a living, evolving antivirus system. In the face of injury or stress, plants can redirect resources through the network, much like our internet routes traffic around damaged nodes. But nature's version is far more elegant. While our networks need complex algorithms and constant supervision to manage traffic, the forest's living internet achieves this automatically, through simple chemical signals and natural feedback loops. The intelligence of this system becomes even more apparent when we look at how it handles competition and cooperation. In a human-designed network, we typically have to choose between optimizing for individual performance or group benefit. Nature's network seamlessly balances both. Plants compete for resources while simultaneously supporting each other, creating a system that's both competitive and cooperative. Scientists have discovered that these networks even support what we might call forest education. When a young tree is planted in isolation, it struggles to develop resistance to local diseases. But when it's connected to the fungal network, it quickly receives the chemical compounds it needs to build proper defenses. The older trees are literally teaching the younger ones how to survive. This knowledge transfer isn't limited to defense mechanisms. Mother trees can sense when they're dying and will transmit their resources to younger trees, passing on their legacy through the network. It's a form of inheritance that operates at the ecosystem level, ensuring the survival and adaptation of the entire forest community. The sophistication of this natural network extends through its security systems. When a plant is attacked by parasitic species that try to tap into the network to steal resources, the system can identify and isolate these threats. The fungal networks can sever connections to compromised plants, protecting the integrity of the larger system. It's an immune response that operates at the network level. What's particularly fascinating is how the network handles data storage and processing. Rather than centralizing information in specific locations, like our computer servers, the forest's living internet distributes information throughout the entire network. This decentralized architecture makes the system incredibly resilient. If one part is damaged, the network can continue functioning without losing critical information. The applications of these insights are revolutionizing how we think about network design. Companies like Cisco and IBM are studying forest networks to develop more resilient internet architectures. The way fungi distribute resources is inspiring new approaches to cloud computing and data center design. And the forest's ability to handle vast amounts of data with minimal energy consumption is providing insights for green computing. But perhaps the most profound lesson from nature's network is its approach to sustainability. While our digital networks consume enormous amounts of energy and resources, the forest's living internet is completely sustainable. It operates on solar power, recycles all its components, and becomes more efficient over time. It's a model of circular economy that we're desperately trying to replicate in our own systems. The role of fungi in these networks is particularly instructive. These organisms evolved to become network specialists, optimizing connections and managing resource flows without any central control. They demonstrate how simple, local interactions can give rise to incredibly sophisticated network behaviors. It's a bottom-up approach to network intelligence that challenges our top-down design philosophies. Scientists are now discovering that these fungal networks do more than just connect trees, they're also vast information processing systems. When a disease appears in one part of the forest, the network can analyze the threat and coordinate a response across thousands of plants. It's like having a distributed immune system that operates at the ecosystem level. This natural network intelligence extends to problem solving. When resources are scarce, the network can calculate optimal distribution patterns that ensure the survival of the maximum number of plants. It's performing complex optimization calculations without any central processor, using principles we're just beginning to understand. The mathematics behind these natural networks is revealing patterns that could revolutionize our approach to artificial intelligence. The way fungi process and transmit information suggests new architectures for neural networks. The forest's ability to learn and adapt without explicit programming is inspiring new approaches to machine learning. But the implications go beyond technology. Understanding these natural networks is changing how we think about intelligence itself. We're realizing that intelligence isn't just about individual brain power, it's about the connections and relationships that form between individuals. The forest's living internet shows us that intelligence can be an emergent property of network interactions. This network intelligence is also changing our understanding of evolution. We used to think of natural selection as primarily about competition between individuals. But the forest's living internet shows us that cooperation and information sharing are equally important evolutionary strategies. Success isn't just about being the fittest individual, it's about being the best connected. The way these networks handle time is also fascinating. While our digital networks operate at electronic speeds, the forest's living internet works on multiple timescales simultaneously. Some signals travel quickly for immediate responses to threats, while other information is transmitted slowly, building up over generations. It's a temporal flexibility that our networks haven't yet achieved. These natural networks also demonstrate remarkable creativity in problem solving. When faced with new challenges, the network can generate novel solutions by combining information from different parts of the system. It's a form of distributed innovation that doesn't require any central coordination. The security implications of these natural networks are particularly relevant today. As we struggle with cybersecurity threats, the forest's ability to identify and isolate malicious actors while maintaining network integrity offers valuable lessons. The way plants and fungi cooperate to defend against attacks could inspire new approaches to network security. Moreover, these networks show us how to build resilience through diversity. In a forest network, different species of plants and fungi create multiple redundant pathways for information and resources. This diversity makes the network much more resistant to disruption than our relatively homogeneous technological systems. The energy efficiency of these natural networks is also remarkable. While our internet consumes vast amounts of electricity, the forest's living internet operates on tiny amounts of chemical energy. Understanding how nature achieves this efficiency could help us develop more sustainable technological networks. Scientists are now discovering that these networks even have memory. The fungal threads can store information about past events, diseases, climate stress, resource fluctuations, and use this information to help the forest respond to future challenges. It's a form of institutional memory that operates at the ecosystem level. The way these networks handle growth is also instructive. Unlike our technological networks, which often become less efficient as they grow larger, natural networks actually become more efficient with scale. The larger the network grows, the more resources and information it can share, creating positive feedback loops that benefit all participants. This scalability extends to the network's ability to innovate. When more plants and fungi are connected, there are more opportunities for novel combinations of resources and information. The network becomes more creative as it grows, generating new solutions to environmental challenges. The forest's living internet also demonstrates sophisticated load balancing. When one part of the network is stressed, resources and information can be dynamically rerouted to maintain system stability. This happens automatically, without any need for central control or complex algorithms. Perhaps most remarkably, these networks show us how to build systems that get stronger with stress. When parts of the network are damaged, the remaining connections often become stronger and more efficient. It's a form of anti-fragility that we're still learning how to incorporate into our technological systems. The social organization of these networks offers lessons for human organizations. The way mother trees serve as hubs while maintaining connections to many smaller plants suggests new models for organizational structure. It's a hierarchy based on nurturing rather than control. As we face global challenges like climate change and ecosystem collapse, understanding these natural networks becomes increasingly crucial. They show us how to build systems that are both resilient and sustainable, that can adapt to change while maintaining core functionality. The forest's living internet reminds us that nature has already solved many of the networking challenges we're still grappling with. As we develop the next generation of technological networks, perhaps our best strategy is to study and learn from these ancient, living systems. In the end, the story of nature's network intelligence is a story of connection, how countless individual elements can work together to create something far greater than the sum of their parts. It's a reminder that intelligence isn't just about processing power or storage capacity, it's about the quality and quantity of connections. As we stand on the brink of new technological revolutions, quantum computing, artificial intelligence, the Internet of Things, the quiet wisdom of the forest offers us a blueprint for building systems that are not just powerful, but sustainable, resilient, and truly intelligent. The future of our networks might depend on how well we learn from nature's original internet. The forest floor beneath our feet isn't just soil and fallen leaves, it's a living testament to the power of connected intelligence. And as we uncover more of its secrets, we're likely to find even more remarkable examples of nature's network genius. The revolution in network design isn't coming from Silicon Valley, it's been growing in our forests all along.